All right, good morning. What's today, March 20th, 2025, ELEC 1013, Network Cabling, Fanshawe College. All right, so today we'll talk about the practical applications of the optical fiber or fiber optics. We have, this is for the class of 2025. After this lab, we're going to have 3 labs to finish, and we're going to have to divide the class in a little bit, but we'll talk about that in our during our in-person class. Because we can only do so many people for the fiber optic fusion splice, because that has to be supervised, and the rest is going to do the 2 other labs in the meantime while you're waiting for your turn. But we will get to that when we get. I'll just explain that to you in person later this week. Okay. I assume that we have good sound coming through. I didn't do the sound check, but I think we're good. All right. If it's too quiet, too loud, let me know. Okay. So let's do this this lesson here. Fiber optics. Now, fiber or fiber, there are 2 ways of spelling, as I always say, fiber or fiber RE. And there's no rhyme or reason why some companies spell it one way, some companies spell it the other way. So I haven't decided which way I want to spell it. All right, it's one of those things. All right, what do we see here on the first opening slide here? It is basically, you can almost treat it as a patch panel for the fiber optics. What we see here is couplers. Control L for laser. All right, so these are the couplers, or otherwise you might want to call them joiners or connectors. You plug in a fiber optic connector into one end of the coupler, and you plug it into the other end of the coupler. Those wide plugs here, excuse me, they are just dust covers because fiber optics are very small in size as far as the core. Now, the single mode is about 5 microns or 9 microns. It can go actually down to 9, but typically 9 microns, which is 9 millionths of a meter. So that's very small. And the multi-mode is slightly bigger, about 10 times bigger, about 50 microns. 50 microns is the standard for multi-mode, and well, today, and about 9, well, usually 9 microns would be the usual size of the core in which the light travels for the single mode optical fiber. So obviously, what happens is that the dust particles are quite comparable to the size of the core in which the light travels. So if there's any dust floating in the air, and the ferrules of the connectors are ceramic, so ceramic can accommodate become static, electrically charged with the static electricity, and the static electricity can attract dust particles. So whenever the connector is unplugged, it should be plugged in or blinded with, or I shouldn't say the word blinded, it should be covered with the dust covers in order to prevent the dust getting in and possibly blinding the entrance of the connector. Okay. Next slide. Types of cables that we're going to discuss today are going to be the loose tube, tight buffered, ribbon. Those are the cables. We are also going to cover some of the connectors and some of the properties of the fiber optic cables or links, conductors. light conductors. Let's go here with the loose tube. Well, the optical fiber is consists of a core. So let's say that red dot is the core, and that would be the part in which the light travels. Now that core is surrounded by something that's called a cladding. Cladding is surrounding, encasing, hugging. All right. So the cladding part is the next layer, like outer layer, and the interface between those two, which means where one meets the other, it creates a nice mirror effect. So the light stays reflected. So as we know from the first part of the of our class, which you will receive later on in person, is that the fiber optic communication is possible due to the something that's called total internal reflection, which means the light travels in the core, bounces off the edges or the interface points or the interface layer or the interface line where the core meets the cladding. It bounces off because it acts like a mirror, and it stays reflected in the core, and thus is able to travel through the core, not escaping through the core. Now, as far as escaping is, it's possible for the light to escape the optical fiber link. If you bend that optical link too much, then the light can actually escape. All right, so loose tube. Why did I talk about that? The basic structure of the fiber? Because anything else that surrounds that, so here's core, here's cladding, and then anything that surrounds the optical fiber is considered a protection, and the protection that is being used, it's according to the need. So if you are using something like patch cables, fiber optic patch cables, then you will need very little protection because it's an inside environment. The cable is not exposed to the outside elements like rain, heat, cold. Then we don't need that much, protection, but you still need some. Now, if you are running the optical fiber under the ocean, then you obviously will need much more protection. As far as the just to protect the core and the cladding, and also there's things in between. Like for example, this loose tube is it is used for running outside cables. So let me just quickly fire up my board here. I'll show you something. And there are things that you drive by every day and you don't notice them, or maybe you notice them and they don't know what these things are hanging on the utility poles. And now you're going to see them all over the place after what I show you right now. But just my board is firing up here. Yeah, that should be good. Create. There we go. Here's my board. Okay. So sometimes when you drive along the road, on the side road, you're going to see something like this. Here's a utility pole. Here's another utility pole, and they just continue, okay? Now, somewhere here you're going to see thick black cable, right? Just spanning over and continuing. And somewhere, like for example here, you're going to see like a black barrel looking object. It kind of perforated a little bit. and it's kind of hanging on the big wires, and you're going to see a bit of a slack going from that and kind of something like this, and the wire is going that way and another one's going that way. So this thing here is called FOSC, right? Fiber optic splice closure. I have one. We have one in our class. So when we do that, remind me to show you that. So I will show you what's inside of those FOSCs. This is basically a splicing enclosure. Sometimes what you're going to see is you're going to see some kind of a company van. Here's my drawing. Kind of skills here, and here are the wheels, and you're going to see a wire, the black thick wire going inside that van. So that FOSC can be taken out, put inside the van, because if you want to work on fiber optics, you need nice, dry, clean environment. So of course, let me wait for someone to pick up the phone. Hold on. Okay, somebody picked it up. The beauty of online teaching. All right, so so those splice enclosures have to be in a controlled environment in which you can do your work on. Right. So sometimes you take the big fiberglass ladder, take it down yourself and put it in there if you're the technician. Or sometimes I can see some companies have this thing organized in a way that there's a crew that that arrives on site, takes that thing down. While the technician arrives, they give it to him, and then once the person is done, it calls the crew and they rehang that FOSC. So these black thick wires are the loose tube. That's what's inside those big black thick wires. So well, I'm trying to always remember polybutylene terephthalate. Okay, I can't even pronounce those chemistry type of terminology. Basically, it's a very durable artificial man-made material that serves as the outside protection for the cable. Then underneath that here you have that what do you call that thing, number 6? Water swallowable tape. That is an extremely absorbent material. Sometimes you probably could see commercials advertising those things that look like candy, like white candy, and if you put that inside, that's like for camping kind of equipment, camping paraphernalia. That if you drop it in water, it just expands to a huge kind of a cloth. So that's a similar thing. This water swallowable tape, polyester type of a tape, it can absorb a lot of water, because this whole thing is it's exposed to the outside elements. So anything that we can, there's always moisture in the air, always. We need to protect those cables in some way. So the engineers found that this material works awesome for that type of application. And this is what the loose tube cable gets its name from. It has a bunch of tubes, just like, tubings that just travel along, in which the strands of the fiber optic cable are inserted loosely. So loose tube cable. The reason why I did those strings or the strains or the links are inserted loosely is because you want to have a little bit of space around it, because when the temperatures go up and down, materials expand and contract in a certain way. So if and on top of that, if there was any moisture that would get there, it would just crush the fiber. If it's like extremely cold or extremely hot, then well, extremely hot, that would be not a problem. But cold, well, when materials expand and contract, they could crush the wires or the links. So there needs to be some sort of a space. And sometimes there is those tubes are filled with certain type of jelly. Okay, things are cushioned a little bit more. Then there's over here, that white thing is a strength member, just to make the cable, well, strong. This cable is not easy to strip, and it's not easy to work with. So with this one, you have to take your time. And there's some other things. Maybe there's some metal protection, like a metal armor that goes around. Sometimes you have that. It's not very easy to bend that, but this cable is made in such a way you can drive over with your car and nothing's going to happen to us. So it's quite durable. So here is the loose tube cable. Right? That's, oops. That's what you see, like the big black cable strung along the utility poles. So that's what's inside that cable, and later on I'll show you what's inside the FOSC, fiber optic splice closure. And you can see, well, there's jobs in that field as fiber optic technicians here. Right? Okay, next, continuing to the next slide. This here is just a bit of a technical information if you want to expand your knowledge on some of the chemistry of the materials being used. You can go over that at your own time. If you're interested, you can dig deeper. But this would be slightly going off topic. However, since things are being mentioned, I thought I would just insert that slide if you want to continue further, if you're interested. All right, thixotropic, because there's a thixotropic jelly that is filled with those. Thixotropic fluid is one that takes a fixed time to return to its equilibrium viscosity when subjected to abrupt changes in shear rate. In other words, the liquid becomes less viscous, thinner, or flows more easily when shaken, stirred, agitated, or otherwise stressed. The fluid then recovers to its original viscosity in a fixed time once the shear load has been removed. It's a mouthful here, a lot of letters into words and into sentences. Basically what it is that this thixotropic jelly that is inside those tubes is protecting the links or the strings or the strains that from abrupt changes in temperature and physical stress that they might endure. Now, loose tube cable. It is designed for harsh environment conditions in the outdoors. Fiber strands floating loosely in the designated rugged tubes. So this is quite rugged, and the tubes are quite rugged, and then you get some ruggedity from the strength member as well. I think I invented a word here. Material contraction and expansion due to temperature changes will not affect the fiber strands because they're inserted loosely. They do have some playroom to expand and contract and not getting physically damaged due to that, those physical changes. Used mostly in the outdoor long haul installations up to 120 kilometers. Now, when it comes to length of the Well, because this would be a single mode fiber, and the next lesson we're going to get, you're going to know, or for some of us, the previous lesson, you already know what the difference is between single mode and the multi-mode fiber. Single mode can transfer the signal long ways. Now, in some sources, you're going to see 120 kilometers. In some sources, you're going to see 60 kilometers. Some sources, you're going to see anywhere in between or somewhere close to that. Now, it depends on who did the experimentation, and depends who did the research, what equipment that they had at that time, did they have at that time, and at which year that article was written. Long story short is that the single mode optical fibers are designed for long haul. When I was some years ago, when our class, when I was a student, we visited one of the bigger communication providers in our city. We were shown a closet in a communications closet with fiber optic connections in there, and we were told the other end of that fiber is in Kitchener, and we were in London, so that's about 100 some kilometers. That was about 25 years ago, or even more. So then, of course, the technology has improved a lot since then. So I think that 120 kilometers is not such a big problem for a cable, to the fiber optic cable, to transfer a signal. And that's without the need of re-amplification or repeating the signal. Of course, then different sources are going to give you different information. So just keep that in mind. But single mode fibers are designed for long haul installations. This is what the FOSC looks like. See that here? Fiber optic splice closure. Now the one that we have is cut off, a decommissioned one, and it has different. Excuse me. It has a different type of insertion solution of those optical fibers here into it. Although what's inside is quite similar. Those cables are being stripped, and here's that reservoir tray here, and so that some of the not used tubes are being just coiled up or folded and left there for further use, future use. And there are trays, and the cable is being stripped right to the buffer. So there is a core, there is a cladding, and the next layer is a buffer. So they're stripped to the buffer, and then when it comes to the joining of those two strands, because you might want to join some strand that goes 50 kilometers that way and another strand that goes 50 kilometers that way, and the type of splice is being used is called a fusion splice. It's basically like melting those two glass pieces together. And because fusion splice or fusion splicing gives us the least amount of loss at the splice. There are also some that's called mechanical splices that, of course, not recommended here in this type of application because they have a little bit more loss. So, like for example, half a decibel signal splice loss would be characteristic to mechanical splice. Which is not acceptable for that long haul applications. Half a dB is half a decibel is a lot as far as the signal power. Now, I don't think you have studied the decibels and the logarithmic scales and the exponential scales, but I'm just going to give you a little bit of a idea what the decibels are, just to give you some picture on what it means. That's a half a decibel loss or some other number of a decibel loss. With power, when it comes to power, If you raise or lower the strength of the signal as far as power is concerned, I'm not talking about voltage in the electrical wires or current or anything else, the power of the signal. If you raise the power of the signal by 3 decibels, you are doubling the power. So if you have a power, for example, a loudspeaker pumping out music with the power of 100 watts, you raise that 3 decibels. From that 100 watts, it becomes 200 watts. You raise that another 3 decibels, the 200 watts becomes 400 watts, and so on. It goes down the other way too. So if you have 100 watts, lower it by 3 decibels, that gives you 50. And lower that by 3 decibels, that gives you 25. So you get the idea. That applies to power. When it comes to voltage or current, when it comes to electrical signals in copper wiring, the magic number is 6, right? So, but the magic number is 3 when it comes to power. And power of what? Power of anything. Right? So now the signal loss at the splice for the mechanical splice, where there is no fusioning going on, there's no fusion going on, then it's about half a decibel. Signal loss at the splice. Now, when it comes to fusion splice, the acceptable signal loss is 0.04 decibels. I always put my units in square brackets. Right, so that's the most acceptable splice. When we do our fusion splicing in our lab, we are probably going to get something 0.01 decibel. Because the fusion splicer that we have is going to splice the 2 strands of fiber, and right after splicing, it's going to insert some control amount of light in order to measure it actually measures the signals, the loss at the splice. After it has spliced it. So fusion splices are being applied here. Right? So that's what the FOSC looks like, and this is a loose tube cable, and this is a FOSC. Now, from the loose tube cable, we move on to something that's called the tight buffer cable. Now, of course, the main thing with the fiber optic is, we have a core. See here. Let's get a new here. We have if we just look straight into the fiber, don't ever look straight into the fiber. Excuse me. I'm going to tell you that. Don't ever look straight into the fiber, because the light that is being transferred through that is produced by a laser, and the laser produces the light in the frequencies or wavelengths that we are not able to see as humans, but the energy is still there. So if you look straight, and if there's a laser on the other side, it can actually make you blind. So here is the here's the core, here's the cladding, and here's the buffer, which is basically like a type of a jacket, and whatever else goes on the other side, more protection as needed. Right? So what we have here, those strands over here, you can see the core that is 50 microns. How can I tell that the core would be 50 microns? Probably, or could be 62.5. But if it was bought for installations today, what I mean is like 2025, then it would most likely be 50 microns, because 50 microns is multi-mode type of fiber. And how can I tell that this is a multi-mode? It's because of the color of this jacket of this cable. It's orange. If it were yellow, then it's probably, well, for sure, it would mean that these cables or these strands are single mode. So there's a 50 microns, and then there's 125 microns. So this one, okay, well, let me just draw another one. So here's the 50 microns, 50 microns core. Then here is 125 microns, micrometers, microns. And then there is 250. Is it 250? Let me just make sure. Yeah, 250 microns right here. 250. So here is the core. Okay, or here is the cladding. Writing with the mouse, cladding, and okay, here's the buffer, which is basically like a jacket, right? So that's what you see right here. This right here, this buffer. So we strip that, and we either do the fusion splicing or mechanical splicing. We strip that right to the cladding. And then there is 900 micrometers tight buffer. And here's the armored yarn. Packed. Armored yarn, or sometimes Kevlar, is well, the material that's being used in the bulletproof vests. So it's very soft fibers, but if you try to cut it with scissors, it's going to give you a tough time. Still can cut it, but not what you expect. It's going to be a bit harder to cut. And so now this is to be used on the inside applications. Run a wire from one communication closet to another in the inside of the building where there is no moisture from outside, because if there were moisture from outside, it would just enter that armored yarn, and it would freeze, expand, contract. Not a good situation. We would have those fibers crushed. So here's a tight buffer as opposed to loose tube. Yeah. Tight buffer cable, designed for indoor applications, fiber strands packed tightly within the armored yarn and wrapped around the jacket. More flexible, way more flexible than loose tube. Used mostly in the indoor local area network environment, LAN applications. Okay. That's what tight buffer patch cords would look like right here. So this would probably be like a media converter modules. So you have the Ethernet cables plugged in, and the signals being converted from one to another, back and forth to the fiber optics. So those yellow ones that look like they're single mode fiber optics patch cables that are connecting something to something else. Then there's a ribbon cable. Let's talk about ribbon cable for a second. It's basically like a loose tube, but if you arrange those conductors or the strands in like a ribbon type of cables, they take less space, which means you can pack more of them. Right? Ribbon optic cable is arranged into a strip, a convenient solution for space and weight problems. What do you mean weight? Well, the cable with all the protecting paraphernalia weighs some kind of considerable amount. So if you need certain amount of fiber optic cables, then you only have to get, if you're only able to pack them only so many, then of course you'll be able to use less of that whole cable if you can pack more. Right? So the cable ribbons are actually coated optical fibers placed side by side, encapsulated by mylar tape, right here, each of those, similar to miniature version of the wire ribbons used in the computer wiring. Very similar. Yes, it's a ribbon. A single ribbon might contain 4, 8, or 12 optical fibers, and they can be stacked up to 22 high. So that's a lot of fiber that can be. As far as color code, you see those fibers have colors and they're color coded. All right, excuse me. From 1 to 24. Right? You got blue, orange, green, brown. Oh, that looks familiar. And the slate. Then there's white, red, black, yellow, violet, rose. Excuse me, and aqua. And then the next ones after that, from 13 to 24, are the same ones, except you have a black stripe through them, except for the black one, because you can't have a black stripe on the black cable, black color, so it's just reversed, so it has a white stripe. So that's as far as the color coding that goes with the fiber optics. Color code for the jacket. Okay. Multi-mode or single mode. Some of the original ones, or the old ones, or the cable fiber optic cable that connects your stereo signal and stuff like that. So they are bigger ones. It's a multi-mode fiber, and it has the inner core 100 microns and the cladding size 140. So that's an oddball right here. Then some of the original ones installed in 1970s or so will have 62, it will be multi-mode cables, 62.5 microns of the core diameter. And look, then we get some kind of consistency. The cladding gets 125 microns. Now, for the non-military, the jacket color would be orange. Military would be green. Now, here's that. What's that? OM1, optical multimode fiber. 1, because it was developed at some point, so they called it number 1. Then later on, they kept working, the engineers kept working on it, developed a little bit better cable, and they call it optical multimode 2, OM2. All right. So here is the multimodes are becoming 50 micron standards for the core, and they become also standard as 125 microns for the cladding. But OM1 is orange. Multimode OM3 is aqua, and they have slightly different specifications as far as the ability to carry signal. And here's optical single mode 1 and 2, and those are yellow. So yellow jacket is single mode. Orange and aqua, that means is multimode. And here's the military coding. If you get into military, you're going to get extensive training as far as what goes with what. Now, remember this thing here. That's for the copper. Cat5, Cat5e, 1 gigabit, transfer speed, because that's basically what we're interested. Also bandwidth. So this is for the digital signal type of transmission, ones and zeros. And this is how far you can push the carrier frequencies for modulated signals. So, well, we can see that most of the cables, well, pretty much all of them, as far as Ethernet goes, they go up to 300 feet. Some of them with certain specifications, we went over that already. Up to 180 feet and so on. So 300 feet seems to be, although I must say that there's also, a couple of years ago or something like that, the engineers came up with a cable that is called a game changer. The name of the cable actually is called a game changer. And that can carry, I think it can carry Cat6, 10 gigabits, up to 1,000 feet, somewhere there. Right. So it truly is a game changer, because forever we were limiting ourselves with 300 feet end-to-end Ethernet cable. So that's the Ethernet cable. Now look at this here. This is a little bit different. This is the equivalent kind of a table for the optical fiber. Now, these are not feet. These are meters, and each meter is about 3 feet, more or less, give and take. Okay. Over here was the optical multimode 1. Look, it can carry the signal of 100 megabits per second up to 2 kilometers. So slightly longer distance, further distance than 300 feet. So yeah. Then there's the optical multimode here. It can carry that with 50 microns, 125, 50 by 125. So that's a core size diameter, and that's the excuse me, that's the cladding. So 1500 here. Okay. Then 1 gigabit. It can carry up to 300 meters, so a little bit less than 300 meters. But then the optical multimode 2 can carry 1 gigabit to 500 meters. So that's how you read that. Optical OM3 can go 1 gigabit per second, 800 meters. So that's a lot more also than 300 feet. And so on. This is how you read that kind of this chart. And here's that big blue. Let's not forget that this exists. Single mode, OS1, OS2. Whoa, it goes about 100 kilometers or so. It can carry 100 gigabits per second. Quite further. How far? Different sources will give you different information. That's why there's that question mark here. All right, now, how much time do we have? We have still some time. Single mode cable is a single strand of fiber, so you can read that. We already talked about that. Usually it has one mode of transmit. That we'll also talk about during our in-person class for the 2025 class here. I will explain that thing to you. You can read that. You can pause the video if you're not part of our class and you're watching this thing 10 years from now. All right, so connectors. Mechanical coupling. Remember the first slide? These are the connectors, what do they look like here? There are different connectors here. SC, standard, stands for subscriber connector or standard connector. Different people call it different way. It has housing. It has a ferrule, just like the pencil. From the beginning to the end, it does have that ferrule. It's like a tubular passage that goes from here right to where it meets the optical fiber, and they're just brought together, aligned with some sort of called index matching jelly for the light to have easier time to transfer from one piece to the other. And that's what the connector looks like. They're being used as patch cords. You can read all that if you want. These are the connectors that are being used. Now, there's SC. Then there's LC connector, which is much smaller in size, does the same thing, but because it's a smaller connector, we can pack more of those on the patch panel and thus save space, because some of the LAN rooms where the fiber optics being used, they are huge and they contain a huge amount of connections. So if you can save some space, yeah, well, it's a bonus, right? So that's this LC connector, lucent connector. It was developed slightly later, but both of them are quite popular. This ST, straight tip connector, that is old. Sometimes you have to use them because you're dealing with the equipment that was installed in 1970s or so, and because fiber optic doesn't corrode like copper does, A lot of the cables that are installed long time ago, there's nothing wrong with them. They can just, they still keep working as they were. Typical wavelengths. All right, let's just go over some of that. While it's common to use frequencies in hertz to specify transmission bands in radio communications, optical fibers, there's a tendency to use the wavelengths. You can do one or the other, but wavelengths in nanometers, you're going to hear a lot when it comes to the different colors of light. All right. Typical wavelengths. Optical communication relies on transmitting the signal in from the light through a translucent medium like a glass or plastic. Yes, there are some plastic fiber optics, but glass is we're interested in right now. Ideally, the scenario would seem as following. Shine the light through the glass rod and receive it on the other end. Well, in reality, the efficiency of the transmission is related to the wavelength of the light. Different colors behave differently inside that glass fiber optic conductor. What we are concerned with is attenuation, which is basically the further along you like for example, if I'm standing beside you and I'm talking with my voice, you're going to hear my voice at certain strength. Then if you stand, let's say 100 feet further, then my voice is going to get attenuated, weakened. It's going to get this not distorted, but it's going to become weaker as it travels further distance. So that's the attenuation. Scattering and absorption are our, well, I would say enemies when it comes to transferring signal over the fiber optic. And we'll talk about those. Now, here is the little bit of a chart of attenuation here and wavelengths. And here is this line here represents scattering amount, and here absorption. Those are bad. The absorption, what does it mean? Those the peak of the absorption peaks, and they occur somewhere between 850 and 1300. The light is completely being absorbed by the link, so you won't even see it on the other end. So that's what it means, absorption. Scattering is that when the light hits certain particles, glass particles, water particles trapped in there, and it's just, or some molecules, and the light just scatters. As always, if I go a couple minutes over time, you may catch the end of it when I put it on YouTube, which is going to be very shortly. So if you have to go to another class, go ahead. Okay. Now, scattering is that when light hits certain type of molecule and just bounces off of it and just scatters in all different directions, also preventing the signal or a large amount of the signal going through, passing through and appearing on the other end of the transmission line. Okay. So let's take a look at here. Here's the amount of attenuation. So here are the high frequencies because they are shorter wavelengths. Here are the lower frequencies because those are longer wavelengths. So here's the low frequencies. Here are the high frequencies. It's kind of, but as far as the nanometers, here's the short wavelengths and there's the longer wavelengths. So this would be more towards blue and ultraviolet, and over here will be towards red and then infrared. Actually, this whole thing is infrared region, but if you travel that way, you're going to hit red. Okay, and then you're going to hit all the other colors, and you're going to hit some violet and ultraviolet. Okay. So around the 850 with nanometers, which is already in the infrared region here, the scattering is high. high frequencies, high frequencies, they tend to be susceptible to scattering a little bit more. Now, when the frequencies get lower, which is the wavelengths get longer, the scattering seems to be less and less and less. So the light passes easier through the transmission line. Now, the typical wavelengths for transmission would be 850, 1300, and 1550 because they are not affected by the absorption. You want to try to avoid these frequencies to transmit, the light pulses frequencies to transmit through the fiber optic link, because over here they are just, the light is going to get absorbed. Over here the light is going to get absorbed. So ideally this seems to be the best region here. The scattering is low and there is no absorption. Those the absorption of the light, the reason for that, the cause of the absorption is that no matter how hard you try, that's the idea, that's the explanation, it is extremely difficult to remove all the water particles. There's always going to be some, even very little moisture in the air, and it's going to get trapped during the production of the glass. And those water molecules are the ones that are guilty for that absorption. So that's the frequency bands here. They're called water bands because of what I just explained to you. Okay. Now let's continue that a little bit further. Scattering, attenuation. So I just optical fiber light signal, it gets attenuated significantly less in the infrared region. It's somehow the high frequencies have a hard time passing through glass, or harder time passing through glass than the lower frequencies. The lower frequencies go right through quite easily. So obviously the lower frequencies, longer wavelengths, in the infrared region, that's the region of choice of optical fiber signal transmission because the waves travel easier through that. Right? Now, scattering, see the blue dotted line. That's the blue dotted line right here. Certain wavelengths interact with the silica modules. Okay, someone picked it. Thank you. All right, so scattering, see the blue dotted line here. Certain wavelengths interact with the silica modules in optical fiber. This interaction results in light being scattered along the transmission pipe or line and becoming unreadable as a signal right here. Now, if the scattering is high, then you're going to have very weak signal going on the other side to none maybe. But when the scattering is lower, you're going to have a nice, good, strong signal appearing on the other side. Now, absorption, the loss happens when the light gets locked in by the water molecules, absorbed by the water molecules that are unintentionally trapped in the optical fibers. See the green peaks marked right here on the top of the graph. Regions under these peaks are called water bands. Transmissions using wavelengths under those regions should be avoided. Typical water peaks occur at 950, 1380, and 2730 nanometers. More info. Now, there's always a but, right? But as technology progresses, the fiber optic industry is implementing RWPF and ZWPF. For our American friends, would be ZWPF. Okay, hello. Reduced water peak and zero water peak fiber are considered as full spectrum transmission lines. Yes, the engineers have come up with fiber optics that have those water absorption, those absorption regions eliminated, and they are called full spectrum transmission fiber. Right, typical wavelengths. Continued. Optical fiber. So for those reasons, primary transmission wavelengths would be 850, 1310, and 1550 nanometers. This would be the frequencies that we want to, or the wavelengths that we want to use because of that. Industry implemented typical wavelengths. All right. I'll have to explain what graded index is to you. So plastic fiber fiber optics. Well, typical 650 and 850 nanometers. This would be the cables that you connect for your stereo equipment or your computer equipment for low type of transmission here. Considering just the sound is not as sophisticated anymore to get a good quality sound. You don't need that high technology of what's available now. Now, single mode and multi-mode and graded index. Typical wavelengths would be 850 and 1300, and for the single mode fiber, typical frequencies are listed right here. Now, what is a graded index? Is that the last slide? Yes, that's the last slide. So let me just explain a little bit what graded index is. Here, if you are looking for on the optical fiber sideways, let's say, and this applies to the multi-mode. So over here, I'm just gonna huge magnification of the core, and this between here and here is 50 microns, and here is a cladding that's 125 microns, and that basically is our fiber here, okay? So when you insert the light with different modes, what is a mode? A mode is a light beam at a certain angle. So if you have a light bulb, all right, that's a light bulb. How many modes does it have? Well, it has infinite number of modes because it just transmits the light all around. Over here, also going to have infinite number of modes, but let's say you have a LED that some of the light is going to go in a straight line, so that's one mode. Some of it is going to go a little bit like that. Some of them is going to go a little bit like that. So some of the light is going to travel in a straight line. Okay. Maybe I should change the color here. Just going to have that so I can come back to this color, so I can just pick the color. Okay, that's good. Let's say there's a light traveling a straight line, so that's one of the modes, one of the beams. And some of them are going to go like this, okay? Bouncing off the core, bouncing off the interface between core and the cladding. And some of them are going to go even harder angle here. I'm exaggerating here, but all right. So the light beams or the light modes, the one that travels at the straight line is going to get to the destination faster than some other modes that have to cover more distance. So it's going to take them longer time to reach the end of the transmission line. So if you have a signal, nice and sharp signal at the input of the transmission line, you're going to have something like that signal dispersed a little bit because you're not going to get that same sharpness out of it. Now, so the core has higher index of refraction, which means the light travels slower than it would travel in the cladding. That's what gives us the mirror effect. Yes, not a mistake. The light is made to travel slower in the core than in the cladding. The cladding is made with the lower refractive index or index of refraction, which we'll talk about, some of us will talk about next time, and which some of us will already talked about it. So that makes that other surface slippery to the light. And if it's slippery, it just bounces off. That's as close as I can metaphorically explain to you. Right? So when we introduce a hard change, sudden change from one type of material to another, and both of them are glass, it's just this, it's extremely pure glass, except the core is doped with some impurities on purpose to make the light travel a little bit slower in it. And it doesn't take much. It's just 1%, 0.5%, difference, and it's enough to create that mirror effect in there. But when we have the hard interface here, the light kind of travels that way. Now, when we have graded index, we gradually change the index from the middle of the core towards the outside diameter of the core. So the index change of the index of refraction is not sudden, it's gradual. What does that give us? It lets us slow down the middle. So here's the greatest index of refraction, and it just decreases as we go outwards. So what happens is that this slows down the line that goes in, the light that goes in a straight line. It slows it down a little bit. So the other light beams or light modes that are traveling, bouncing off, can catch up. So at the end, instead of having a very dispersed or quite dispersed signal, you're going to get something more similar to what you had. You're going to get something closer as far as sharpness of the signals, which means you can have transmissions that are more comfortable, and when it comes to transmitting signals on the other end, to the other end of the fiber link. So that's what graded index is. Over here, multi-mode, because multi-mode cable can come with just regular multi-mode link, or you can have graded index cable. All right, so that's okay. That's it for today. 2025. This is Thursday. I'm going to see some of you tomorrow, Friday. Some of you lab and some of you theory. Cool. Thank you very much, and I'll see you when I see you.